Hello everyone. In this lecture today, we continue this integrated optical components. We have been discussing for several lectures important component like a distributed Bragg reflector, and based on that, basically this is a distributed perturbation in single mode or multi-mode waveguides typically, and using that type of structure. Normally several important device could be designed and can be achieved a lot of important functionalities. So, first we will try to discuss today how to estimate penetration depth. So, you know it can be a DBR structure like this, very long structure you can make. You can make maybe 10 micron, you can make maybe this one maybe 10 micron, this one can be 25, can be 100, can be 500 microns or so on. But important question is how long this grating can be. Normally, typically if you consider integrated photonics for large scale integration, so footprint should be as small as possible. So, smaller the length, it is always good for compact photonic integrated circuits. So, we should know, we should have a knowledge that how much maximum grating length we need to get, so that at least we can get reflectivity in the order of say 100%, nearly 100% I would get. Okay. So, that is how it is our understanding. With this understanding, we will be just trying to learn how to estimate that penetration depth inside the grating. That means a particular lambda, say lambda b for example, Bragg wavelength. I know that any electromagnetic signal propagating in the waveguide, because of the periodicity, and it is phase matched to lambda b, so that it will be reflected back. But this reflection cannot happen exact at the beginning. It is distributed, reflection is distributed. So, that is why it is very important to know how to derive the penetration depth or penetration length. And then based on this principle, penetration length etc. and stop band concept of a periodic structure, I will try to give a overview on how a photonic crystal waveguide works. Specifically concept of photonic crystal waveguide, that is also an important component for photonic integrated circuit. I will show some example how this photonic crystal waveguides can be useful for certain active and passive device design. And then third topic is the how one can use this DBR, distributed Bragg reflector, to design an integrated optical Fabry-Perot cavity. Perhaps some of you might be knowing what is Fabry-Perot cavity, but in spite of that, I will just give you some overview, the working principle of a standard common Fabry-Perot cavity, and then how that Fabry-Perot cavity can be designed with a DBR structure which can be actually integrated in a photonic integrated circuit. Okay. So, that will be discussed, and finally, I will be discuss how to design add drop multiplexer. That is a very important device component used in fiber optic communications. So, sometimes it is also useful to have certain such device add drop multiplexer on chip for optical interconnect purpose. So, I will be discussing that one. So I again I reproduce this DBR structure: input waveguide, single mode waveguide, output also single mode waveguide. In between you have a DBR structure of length L, z equal to 0 to starting to z equal to L. And also in this DBR structure we know that there will be forward propagating wave, associated electric field is EF XYZT, and backward propagating wave EB XYZT. So, if it is a single mode, both forward propagating mode profile, field profile, and backward propagating mode field profile will be identical. So, that is why we just consider that forward propagating wave can have some kind of slow amplitude modulation along z direction. Slow means because of the weaker perturbation, I would say. DBR structure is designed with a perturbation, which this perturbation, periodic perturbation, is not so strong. In that case, we can say slowly varying. And E naught xy actually basically your mode field distribution for the fundamental mode if it is a single mode waveguide, and forward propagating wave we can estimate our phase, time dependent as well as position dependent e to the power j omega t minus beta z. Similarly, backward propagating wave, you have your amplitude modulation as a function of z, variations that is also slowly varying, and since it is backward propagating and single mode waveguide, the field distribution, field profile for the mode are same. Consider only thing is that the phase part here, that is actually, since it is backward propagating, we have just added plus. And we know that phase matching condition, to satisfy phase matching condition, which is essential for sufficient coupling, significant coupling, we find a parameter called delta beta, that means phase mismatch parameter. We have derived earlier, that should be angular frequency omega 2 times omega by c, n effective omega. N effective omega is the guided mode effective index at operating at frequency omega minus 2 pi over lambda. So, delta beta equal to 0 means it is a phase matched condition. So, coupling will be maximum. And we just reproduce again to understanding for understanding purpose, that if your forward propagating mode amplitude, that slowly varying z dependent amplitude, and backward propagating amplitude, if they are coupled, then we could derive coupled differential equation, which can actually give us a idea about amplitude evolution along the grating length z. So, two equation, coupled equation. So, kappa we know, kappa is the overlap integral. So, basically how grating is overlap with the field distributions of the forward propagating wave and backward propagating wave, that using that one can estimate kappa. And kappa star, it can be complex. If it is complex, then one will be minus j kappa a2 e to the power j delta beta z, this is the delta beta, and in case of backward propagating wave, it will be plus j kappa star complex conjugate, and of course it is coupled with a1. So, that means the evolution of a2 mode is happened because of the a1 here, and here also in turn we can say that evolution of a1, that means forward propagating mode, that can also be associated with the backward propagating mode, a2 is there. So, these are coupled equations. So, to solve it, we could actually, earlier also we have shown that we can eliminate from these two equation that a2, and we can find a second order homogeneous differential equation only for a1. Similar equation we will be able to get from a for a2, that will be actually equal to dA2 by dZ2 minus j delta beta dA2 by dZ minus kappa square a2, that should be equal to 0. Another equation we could write down. I have just written one because it is obvious for the other. So, we can just get this equation, and here we have considered, of course, for all these equation delta beta equal to, instead of this one we can write that 2 omega by c, this one basically equal to beta. So, that is what we written 2 beta minus 2 pi by lambda. Either you can write this in terms of beta, or you can write delta beta in terms of omega. By detuning omega from the phase matched frequency, you can get significant variation in delta beta from 0, and if it is varying with delta beta is very large, then we will be seeing that the coupling will not be that much significant. Okay. So, from here we know we have solved earlier. I am just reproducing again that if you just follow standard second order differential equation, homogeneous differential equation solutions, the solutions will be, we will have basically two roots. One first component will be e to the power j delta beta by 2 z minus sz, and this will be z plus sz, where s defined by this. Okay. So, that is straightforward. We have solved earlier, reproduced here. Similarly, we can get for a2 will be in this form. Okay. So, I can get another differential equation, second order differential equation for A2, and then A2 can be solved also similar way. Only thing is that plus j minus j, that will be the difference here you will be getting. But here you see this minus plus and minus plus, because of the roots are plus minus coming, it is a complex, one real part, another imaginary part, based on that you will be getting. Now, next thing what we do, we can say that this, if this is the A1 jet, then we can write down this forward propagating wave EF Z dependencies. You know, Z dependencies, one factor is here, another factor is here. So, we can club them together, right. We have the A1 jet, that is directly written here, along with that e to the power j minus beta jet, that we are writing as a Z dependent evolution including phase in the forward direction. So, here also some certain kind of phase will be coming, because exponential and imaginary part is there. This can be written as, if you just do little bit of maths here, this EFZ can be written as CF e to the power minus beta prime z, where beta prime can be written as this one. Two values you will be getting, one for plus, another one for minus. So, instead of two different solutions, linear combinations, we are writing in a compact form with beta prime has two different values, one corresponding to e to the power minus j beta j, you add with this one and another one with this one, then you will get one will be plus value, another will be, one will be plus sz, another will be minus sz. So, beta prime can be expressed, two different beta prime we can get, and their linear combination will be the solution for forward propagating mode, and it is just shown as a electric field. So, magnetic field will be also identical. Similarly, we can think of backward propagating wave including the e to the power j beta z. So, we have the backward propagating amplitude A to z is this one, written this one, and you multiply this one, then you get backward propagating wave also in this form. Again, this beta prime will be same. So, it is something we can have this forward propagating wave with a modified propagation constant, I would say, and backward propagating wave also has a modified propagation constant, same but in the backward direction. So, with these two solutions, we could say that the perturbation earlier in analyzing normal DBR structures, weak perturbation we consider, and we have assumed that the forward propagating wave and backward propagating wave, they are weakly disturbed and their propagation constants are considered same, but we have the value of A1z and A2z that is coming as a complex z dependent, and that z dependent part if you just include in the exponential term here, then I see that as if it is a kind of wave which is actually propagating with a modified propagation constant beta prime. This is some through our mathematical analysis we can say that beta prime certain value is coming, it is a modified propagation constant because of the perturbation I would say. And you see this has to be multiplied by e to the power j omega t, and this has to be multiplied by e to the power j omega t, and this has to be multiplied by e naught xy, which is actually considered same e naught xy, then you would be getting complete solution like this. Okay. So, now what? Now, we can slightly modify this beta prime. Okay. So, here beta prime is this one, right, after modification of this one. Now, we can just do delta beta value here, we know this one, right, delta beta value is there. So, we can write beta prime equal to this beta value along with delta beta value. I just put down here delta beta value, okay, and also S. So, I can say that here, for example, beta value equal to delta beta by 2 pi by lambda minus. So, pi by lambda, and I have pi by lambda delta beta. So, you have another delta beta 2 that will be cancelled. So, beta prime can be written down like this form. If I just substitute S is given by this one. So, I am just putting S value here, and beta minus delta beta by 2 equal to pi by lambda. So, that is what beta minus delta beta by 2 equal to pi by lambda. From this equation you are getting that is pi by lambda, capital lambda plus minus j over this one. Now you see this equation, try to see this equation, pi by lambda is a real value, plus minus j, that is actually j is the, this part is the imaginary. Okay. Now if delta beta by 2 or delta beta mode less than 2 kappa, delta beta mode less than 2 kappa, then what happens, this one will become positive and j will be there. So in that case you will have a complex value with some beta prime will have a complex value with a imaginary part, right. So normally when we consider a electromagnetic wave propagating along a homogeneous medium, we consider alpha j beta, that is actually propagation constant, this real part contributes loss and imaginary part contributes your propagation constant. Here beta prime itself is again becoming complex. It has beta considered as a real, normal waveguide mode, the beta is a real value. Now because of the perturbation we modified, we have a modified propagation constant which can be imaginary when delta beta, that means phase mismatch constant factor, which is lying within 2 kappa according to this expression. So when it is imaginary, what does this mean? This means within stop band beta prime is a complex for wavelengths within the stop band. When this one, this is the condition we found. Now because of that, what we have, the penetration length is defined by LP equal to, that means what we said that the electromagnetic wave or forward propagating wave or backward propagating wave, both actually it will be attenuated along DBR because of the imaginary part. Now because of the imaginary part, this imaginary part you know, normally you have imaginary part, it will be a j beta and beta will have z, and then e to the power j beta z, and you have suppose alpha, suppose a plus jb is there z, then what will have, e to the power minus bz and e to the power j az. So now a will become your propagation constant and this b factor, the imaginary part, that contributes the exponential decay. So according to this expression, both forward and backward propagating waves exhibit decaying along plus z axis. So if I forward propagating wave, if it is initially it is a 1, then it will be decaying along z direction, it will be following, and then from here up to here it will go, and backward propagating wave also it will be building in backward direction, but along positive direction. If you see, this is also decaying and this is also decaying in nature. If you just see along positive direction, you just match the amplitude of the electric field, associated electric field, then you will see both are reducing along positive z direction. Okay. So that is what it is mentioned, that decaying part, if it is decaying exponentially, according to this thing, it seems like it is decaying exponentially. So anything decaying exponentially, right, so that we can consider as a some kind of after a certain length, that field amplitude will be significantly reduced. So in that case we can consider this b in this case is this one, right, and we know if z equal to something like this, I can consider z equal to LP equal to this one, z equal to LP equal to this one, then what happens, the field amplitude will be attenuated to 1 by E. So you know 1 by E penetration rate, that means in the surface if it is 1, so after LP distance, suppose LP distance here, so z equal to LP, there the amplitude will reduce to 1 by E because of the nature of the attenuation we have discussed, beta prime becoming, propagation constant becoming complex, having an imaginary part. So that is actually called penetration depth. So that penetration depth can be calculated 1 over this one. So if this is your B, so called imaginary part of the beta, that imaginary part, you know, this inverse of that one can be considered as a length at which the field will be attenuating to 1 by E, right. So if you consider if it is a Bragg wavelength, then delta beta must be equal to 0, phase matching condition. So, when delta beta equal to 0, whatever lambda you can find out from here or omega you can find out, that is a Bragg wavelength. So, in that case delta beta 0, then what we will be getting, LP lambda b equal to 1 over kappa. So, that means if you know coupling strength of a DBR structure which you can calculate, then you can find that 1 over kappa length will be the Bragg wavelength. Any electromagnetic wave operating at Bragg wavelength, that will reduce to 1 by E. So, now I know the knowledge of penetration depth. So, accordingly I can say that okay, my DBR structure can be little bit higher than the penetration depth, then we can see that significant amount of reflectivity I can expect. If this delta beta is deviated from 0, delta beta not equal to 0, suppose delta beta not equal to 0. So, in that case what will happen, you can get certain value is less than kappa, that means LP will be longer. So, Bragg wavelength will be the electromagnetic wave operating at Bragg wavelength that will penetrate less. As it is going away from the Bragg wavelength both side, if delta beta is having some value, then it will penetrate longer. So, if delta beta tends to very large value, so in that case you can consider that okay, that is far away from lambda b and that will be penetrating up to infinity and that will be passing through that. So, this is a very nice way of representation, how much to estimate how much DBR length you supposed to have for your photonic integrated circuit. Okay. So, this is a good example. Now, let us try to see how this DBR structure, the concept of DBR structure, what we understand from the concept of DBR structure. So, we have learned that there is a stop band, you can express in omega or you can express in lambda SB, stop band I mean to say, stop band around lambda b or around omega b. You will see that this is decaying almost like a evanescent field, meaning that particular within that particular band it is not allowed through the DBR structure because of the periodic structure and phase matched wavelength, so called Bragg wavelength lambda b. Around that you have a certain band, we have already shown earlier how to calculate that. That particular band will not be allowed. It is evanescently decaying, means everything is getting reflected in the backward direction. Significantly it is reflected in the backward direction. The same concept, it is a kind of periodic structure, it is like a we can call that as a one dimensional photonic band gap structure. If it is a DBR, I can say that normally you know semiconductor, you have a conduction band, valence band and we have a band gap where electron energy is not allowed. So, here also that is happening in crystal because you have a periodic structure, periodic atomic structure is there, that periodic potential that actually created by the nucleus of the atoms actually is reproduced analogously in case of a waveguide structure with a periodic perturbation. Here periodic perturbation means periodic dielectric constant. So, periodic dielectric constant is perturbed periodically, as if similar to electron it is a potential is perturbed because of the presence of atomic nucleus. So, presence of atomic nucleus produces stop band for electron. That is how you get conductor, semiconductor, dielectric, where band gap actually defines. If it is there is no band gap, the conduction band, valence band almost overlapping, that is a metal, and then if there is some gap is there between two bands, then it is called semiconductor, and if it is this bands are widely apart, there is a large band gap, then that is called dielectric material. So, similarly here also, if I make some periodic perturbation in terms of dielectric constant or refractive index, then you can say that certain band of energy around Bragg wavelength will not be allowed. So, it is a band gap. So, here also we have a periodicity, that is why it is called kind of crystal but it is a photonic crystal. It is not the crystal like a real crystal we know, that is a crystallographic structure we learned, but here also we are getting a crystal like structure, but in one dimension, and even one dimension a guided mode with a certain band of frequencies will not be allowed, stop band. So, this particular concept actually you can use for developing a special type of waveguide called photonic crystal waveguide. That there are various type of photonic crystal structure. There are 2D photonic crystal, 3D photonic crystals for various application. Theoretically, a lot of thing it is analyzed, a lot of interesting phenomena could be achieved using a periodic dielectric perturbation that can be 1D, that can be 2D, that can be 3D. In this case, it is a 1D photonic crystal. DBR structure can be considered as a 1D photonic crystal structure. So, the photonic crystal structure can be, if it is the periodicity is in 2 dimensions, 2 directions, equally periodic or maybe not equal also, that is also called a 2-dimensional photonic crystal. If the periodicity, dielectric constant periodicity, you can manufacture also such material in all 3 dimensions, there is a periodicity exists. So, in that case that will be called as a 3D photonic crystals. But we will be discussing the very important waveguide structure. One of the important waveguide structure, working principle is completely different. So far we have learned how the waveguide theory and their guiding modes we have evaluated. It is based on, we know that is based on total internal reflections, right. So, in this case we will be just coming up with a new type of waveguide structure based on the stop band. That means a certain band will not be allowed because of the periodicity. Okay, that is actually well known at, and a lot of interesting device components, integrated optical components have been demonstrated for certain advantages. I will just explain qualitatively how those type of photonic crystals are realized for planar integrated circuit, photonic integrated circuit. You see, this is a 3-dimensional structure. This is your box layer, maybe silicon dioxide, okay, and then here in the bottom you have a silicon substrate, okay, that can be 500 micrometer thickness, and this can be about 2 to 3 micrometer thickness, and device layer in the order of 100 to 250 or 350 nanometer device layer thickness. So, this is actually silicon dioxide, this is again silicon, okay. So, now what you can do, you can have a periodic structure, you can make periodical hole in the device layer. This is device layer, periodic hole. Here it is shown that one, this is the, you see, hole, and then another hole, you can consider this one is the period here, okay. So, that along this line if you see, it is a periodic structure, periodic holes are there. So, along this direction you can see that, if you are just forgetting all other direction, you can say that it is identical like a DBR structure. So, if you consider also this direction, it is also identical like a DBR structure. Any other direction you consider this direction, it is identical like a periodic DBR structure. But in this case what we see that this DBR structure is there, but in a planar way, 2-dimensional periodicity is there, okay, 2-dimensional periodic holes. But in our conventional DBR structure what we have? We have a waveguide, and along the waveguide periodicity is there. So, that's why DBR is 1D, in this case 2D. So, what does it mean? If you see that any light try to escape this direction, suppose you have a source somewhere here, somewhere you have a source here. If it tries to escape this side or this side, everywhere, because of the periodicity, it can see that that particular frequency, if it is falling within the stop band, that will not be allowed to go in this direction, in this direction, in this direction, in this direction, nowhere. It will be trapped if all the boundary condition is actually satisfied. However, if you make a defect line, this is a defect line. If you see, this is one line and one line, next line little bit shifted, it is a hexagonal lattice structure. If you see this one, this is something like a hexagonal structure, okay. Anything you consider, and the center will be one thing is there. So, hexagonal structure, if you see one defect line is created here, just broken the periodicity there along this defect line. So, in this defect line, if you have a guided mode, if you are launching here, if you are having certain light, you are entering, you are just coupling here, then what happens? This light cannot be escaped in this direction, in this direction, in this direction, in this direction, because all direction you see stop band. It is not allowed. It is like a DBR structure. However, if it is possible, if it has a wave vector only in this direction, it is possible that it will be guiding. Other direction it will be restricted. So, in this way you can see a guided mode along the defect line. So, light can be coupled here and can be confined along this defect line. Lateral direction it cannot escape because of the photonic crystal band gap. So, photonic crystal band gap actually not allowing your electric field or electromagnetic wave propagating in that direction. It is like a evanescent field. We have seen that in total internal reflection also evanescent field is there, it is a decaying field will be there, and here also because of the photonic crystal it is like a DBR structure you have seen that stop band it is decaying exponentially. So, it will be decaying this direction, decaying this direction, but it will be oscillating, propagating in this direction as a mode. So, this is how one can think of confinement along this direction. If this is x and this is your y and this is your z, so along x direction you have a confinement because of the two-dimensional photonic crystal and a defect line. But what about vertical direction? Vertical direction still it is 220 nanometer or 250 nanometer thickness and it is lower refractive index. This is your so-called substrate and this is called device and this is called cover. So, all these ND greater than NS greater than NC. So, vertical direction can satisfy total internal reflection because ND greater than NS NSC. So, vertical direction you can have a mode confinement because of the TIR, total internal reflection. If possible, you can also make a trench here. You can remove this oxide in the defect along the defect line. This oxide if you remove, then it will be just NAR, right. So, along this line, so you can say that vertical direction light will be confined because of the total internal reflection and horizontal confinement due to photonic crystal band gap. So, you can have a guided mode. So, one advantage here is that in the photonic crystal, we will show later that any mode guided through this defect line or even in the DBR structure, in transmission that guided mode will have a NG very large, group index is very large, guided mode group index becomes very large, much higher than the normal strip or photonic wire waveguide structure. That means the group velocity C by Ng is lower, smaller. So, light can be traveling very slow. If you can design a suitable photonic crystal structure, the light velocity, group velocity can be reduced 30 times, can be reduced 100 times lower. That means a guided mode will travel very slowly. So, when a guided light travels slowly along the photonic crystal waveguide, it will interact more, it will take more time to interact with the material. So, that interaction enhancement is helpful for certain device applications. I will show one example here. Recently, I think not recently, in 2010 demonstrated by Chi-Yun Lin et al. And published in a journal Applied Physics Later, American Institute of Physics journal, where they have used a, you see this is a structure, this is the waveguide and a special type of spot size converter, so that you can couple light into the photonic crystal waveguide along the defect line. So, light will be guided through this one here. It is a special type of waveguide that horizontally it can be confined because of the photonic crystal band gap and vertically it can be confined because of the fact of total internal reflection as I explained here. But here instead of simple defect line, there is a slot created here. that is called slot waveguide. Okay. Whatever that slot waveguide, I will be just explaining very quickly qualitatively. There also a guided mode will be there, and that guided mode also can travel very slow, and so that it can actually get more interaction with the material, more time for the interaction. So, what it is done, when they have created holes, on the top of it they have just poured certain kind of polymer. This polymer actually very much good in electro-optic effect. That means, if you apply a voltage across a certain distance with a two electrode, maybe this is one electrode, this is electrode, this is electrode, and you apply a voltage across that, that means you can create an electric field. Since this polymer is a electro-optic material, because of the electric field, you can actually modulate refractive index. If you can modulate refractive index, you can modulate the phase velocity of the guided light. So, you can create a modulator, high speed modulator, electro-optic modulator. You know, silicon is not a good electro-optic material, that is why different type of modulator normally people demonstrate it, and that is actually called your that is why you need to have a photonic crystal structure, and wherever you have holes, there you power polymer, which is actually electro-optic material. Not only electro-optic material, this polymer has a lower refractive index than silicon, but higher than air. So, normally hole will be creating air will be 1, but if it is a polymer, that polymer will be in the order of 2, and refractive index for silicon is 3.5, around 3.5. So, in that case, you can periodic hole structure, actually that will create periodic modulation of dielectric constant, and in this way you can expect stop band along forbidden band along horizontal direction, but it can be guided in this direction. So, that is how the high speed electro-optic modulator with a very low figure of merit, you do not need very high voltage to create a required phase shift, maybe pi phase shift you need for Mach Zehnder interferometer type of modulator. Okay. But as I mentioned, here they have used a special type of waveguide. So, we have discussed the waveguide so far, that is based on total internal reflection, and then based on hybrid total internal reflection plus photonic band gap type. One direction it is confined because of the photonic band gap, other direction it is confined because of the total internal reflection. But another type of waveguide called a slot waveguide. So, that slot waveguide, what it is, you know, suppose you have a device layer, you are creating a waveguide, it is your oxide box layer, and this is your device layer, you have a waveguide, and waveguide to confine, to support a fundamental mode, you need a particular width, below which it may not confine a guided mode. Okay. Similarly, if you want to have another waveguide far apart, single mode, certain waveguide mode, single mode, it can be coupled, it can be guided, and if they are far apart, they will not be coupled. Now, if you bring them closer, if they are guiding individually one mode, then what happens? As they come closer and closer, they interact each other, and we know using that interaction, when they coming closer and closer, because of the interaction, their modes are getting overlapped to each other, and you can actually design directional coupler, and directional coupler is an important component, you know, we have learned earlier. But if you consider this W are not sufficient to guide even a single mode. Suppose a single mode can be guided, say cutoff maybe, W cutoff maybe say around 300 nanometer, and if you create this structure which is less than 300 or less than WC, this is also less than WC. So, independently they will not be able to confine a light. However, if you bring them closer, then what happens? Combined thing, they can confine a light together. A guided mode can expect, you can expect a guided mode. But in that case, what will happen, you know, the electric field inside the so called rib region will be lower, and it will be enhanced just to follow the boundary condition. You know that normally we know that normal component of displacement vector in two media according to the boundary condition, they are equal if there is no charge, and displacement vector, you know, epsilon 1 E1n should be equal to epsilon 2 E2n. Suppose your electric field is oscillating in this direction, you have a, let me see here, suppose you have a structure, okay. Suppose you have a field in the boundary you are considering, this is silicon, epsilon 1 around 10 for example, and this is air, that is actually epsilon 2 equal to 1 for example, right, epsilon 2 equal to 1. Now if you see, if you are seeing a electric field in the boundary, and if you satisfy this condition, then you can say 10 times E1 n, in this case it is a tangential in this direction we are considering, equal to 1 E2n. So that means E2n is 10 times of E1n. That means outside electric field will be 10 times higher strength than the inside. So similarly here, whenever you are just considering a guided mode type of things here, together jointly it is giving a guided mode, because of the boundary condition, you will see in the gap region, in between the gap region where air, lower refractive index region, their field strength will be high. So normally we can say that in a standard single mode waveguide, your core region refractive index is high, where electric field strength is higher. As you go towards the cladding, electric field strength will be reducing and exponentially decaying towards the cladding. But in this case, you see individually these ribs, they cannot support a mode, but when you bring them together closer and closer in the gap region, to satisfy the boundary condition, the field strength will be enhanced, and you can get a mode like solutions. If you solve Maxwell's equation, you will see that some eigen modes will be there, some eigen propagation constant will be there, eigenvalue propagation constant will be there, and as a mode it can guide. So, but that mode speciality is that electric field strength is higher in the lower refractive index region. So here also they have used that type of slot in the center region. So in that slot again they have for polymer, electro-optic polymer. So lower refractive index region, field strength is higher and electro-optic is more, electro-optic effect is more, so you can get more effect on the propagation of the guided mode. So you can get very efficient electro-optic modulator. So that is what they have demonstrated in 2010. Later on, actually in this direction it is a very amazing, theoretically it is very good, you can get a very good results, and if you have a very good fabrication technology, high technology, then you can get a very good periodic structure with smooth sidewalls, then you can get a very low loss device which can be useful. But typically, you know, so many periodic holes are there, and holes in the sidewall, there will be roughness will be there, and that is the reason normally photonic crystal waveguides are lossy in practice. Theoretically it is very good, you can actually bend very sharply for your guided mode, even 90-degree bend is possible, some people demonstrated theoretically, but experimentally normally this type of waveguides are highly lossy because of the roughness, because of the non-homogeneity. Sometimes fabrication related yield is required, that periodic, so many holes, if their periodicity somewhere it is broken, that point it will be leaking. So that will not be very good. So unless and until the waveguide loss is reduced, this type of device will not find much application. So you know, this is actually demonstrated in 2010, but nowadays people are demonstrating modulator with different technology, but not with this technology. It's today in the market available of course, but this type of device could not be commercialized because loss, insertion loss, light from here to here, whatever you will get, loss is very high. Okay. So this is one application, though technology, with the advancement of technology, this technology may come back again. So one need to work hard to develop, improve the technology, process technology, fabrication technology, right. So we have discussed. So now we learned that, okay, in the course of DBR understanding, we have learned 3 different type of waveguides. One is actually standard waveguide based on total internal reflection. Light is confined because of the total internal reflection inside the core, and another type of thing is that light can be confined in one direction because of the 2D photonic crystal band gap structure, and another direction it can be total internal reflection. So, hybrid type of photonic crystal waveguide, I would say planar waveguide structure, planar photonic waveguide structure, and another type of waveguide as I mentioned, that is a slot waveguide. Your waveguide will have a 2 rail. Individually they cannot support a guided mode, but if you bring them together, then you can get a solution of a guided mode and eigenvalue also, propagation constant, and field strength will be somewhere something higher in the middle, low refractive index region, that is called slot waveguide. There are many research, many application, many devices demonstrated, especially for sensing applications. This type of slot waveguide people are using. Good. Now, the another application I would like to discuss, that is DBR based integrated optical Fabry-Perot cavity. So, perhaps you many of you know what is Fabry-Perot cavity. Fabry-Perot, 2 scientists basically, Fabry and Perot, French scientists, they have first demonstrated a cavity like this, and both sides it will be mirror, and mirror reflectivity will be R1 and R2, and then there will be some kind of if you just this R1 and R2, if it is not equal to 1, partial mirror, then some light if you enter, and because of the multiple reflection back and forth, certain wavelength will be stored because of the resonance, and some wavelengths will be out of resonance, that will be passed through. So, in the output you will be seeing something characteristics like this, periodic transmission. It is something like airdrop ring resonator type things you will be getting. So, in that if you just say new frequency and this is the transmission, then you will be getting something like that. That is actually Fabry-Perot cavity, and that Fabry-Perot cavity first time it was used by Maiman, you know, who demonstrated the DBR, who demonstrated first the laser around 1960. Yeah. So, laser demonstration they have used this type of cavity. So, this type of cavity, it was a bulk that time, it is a medium, active medium, and you have mirror both side, partial mirror, and that is how the laser was demonstrated. Not only the cavity used for laser demonstration, sometimes a special filter, special particular wavelength you want to filter, certain wavelength you want to filter, that purpose also Fabry-Perot cavity used. So, we will be just discussing now how this DBR structure can be used to demonstrate a Fabry-Perot cavity. And not only Fabry-Perot cavity, there are many more applications are there. I will be just discussing, very important. So, what is the fundamental requirement to understand those type of devices, I will be discussing now. So, just start with Fabry-Perot cavity bit with a broadband mirror. Suppose this is a waveguide, single mode waveguide, and it has a fundamental mode with a propagation constant beta, and beta, you know, beta is always omega by c n effective, that is why we have written beta is a function of omega. N effective also can be a function of omega. And you can have a forward propagating wave, backward propagating wave. If you have a mirror both side, and the mirror is having amplitude reflection coefficient R1 and R2 respectively. Amplitude reflection coefficient, normally if amplitude reflection coefficient is R, and if you see the RR star, that will be actually power reflection, reflectivity. Okay. So, amplitude reflection coefficient R1 and R2, and they are separated by L. Suppose this mirror is giving the reflection, because it can be complex, it can have some kind of amplitude and it can introduce some kind of phase. Okay. So, that if it is introducing upon reflection, if electromagnetic wave undergoes some kind of phase change, then the reflection coefficient is complex, and that complex reflection coefficient can be expressed like this. It has a mode R1 and e to the power j phi 1. Similarly, R2. So, it should be R2. Okay. R2 equal to the mode of R2 e to the power j phi 2. Okay. Now L, they are separated by L, and this is a waveguide. For understanding purpose, we are just considering a waveguide and separated by mirror. Now longitudinal mode resonance. So to have a resonance, any signal travel this and reflect back, coming back again reflect. If it is one round trip acquiring phase of 2 pi times integer value, then that particular wave is resonant. It can happen for a certain wavelength. So for that certain wavelength, it satisfies that round trip phase shift is 2 pi, then that particular wavelength can be stored. It is resonant. It can go, it can reproduce again this wave, again comes back, it reproduces. It is a yielding constructive interference it is creating. So this is a resonance condition. It is same like a ring resonator, round trip phase accumulation is 2 pi times integer, then it is a resonant wavelength. So here also it is a ring like thing, but you see it is just forward direction. It is going, for example, a ring waveguide, wave goes, comes back here, one round trip. But here again coming back, but in between you have a mirror type things. It is like a ring resonator we have discussed, you have a bus waveguide. So something goes here and comes back here. So this type of add drop multiplexer ring resonator we have discussed earlier, similar type of model can be considered like a simple Fabry-Perot cavity. So mode resonances, longitudinal direction mode resonances, because we are considering longitudinal direction the phase. Round trip phase, if beta is the propagation constant, round trip length is 2L, 2 times beta L, that is the path dependent phase, and then mirror introduces phi 1 phase, mirror 1, and mirror 2 introduces phi 2. So in a round trip it undergo 2 times path, forward direction, backward direction 2L, and because of the propagation constant is beta, multiply that, you get a propagation constant or phase, total phase accumulation round trip, and 2 times reflection. So starting from here, you go here one reflection with phi 2 and comes back another reflection phi 1. So that's why total phase, round trip phase, if you estimate, that will be 2 beta L phi 1 plus phi 2 equal to 2 m pi. M equal to can be 0, 1, 2, 3, 4 depending on the phi 1 and phi 2 value, right. So if you just proceed a bit, just assumption, you just consider that okay, this is something a standard mirror, metal mirror, most of the time it does not give any phase shift. So if phi 1 and phi 2 equal to 0, then what we get? 2 times beta, beta means omega by c n effective, this is beta times L, that should be equal to 2 m pi. And in that case, m starts from 1, 2, 3, not equal to 0. If it is 0, then everything is 0. That means omega equal to 0 has to be. L not equal to 0, omega has to be 0. That is why we are avoiding. But in this case, m can be 0 considered if phi 1 and phi 2 are negative values. Phase shift can be negative. Okay. So now 2 times omega by c n effective omega L. What we do here, this you just differentiate with respect to omega. You see L by c we have kept here. Now if you have omega times n effective omega, if you just differentiate with respect to this, with respect to omega, d omega, for example, if you do, then what you get? N effective, you just differentiate with respect to omega, that is 1, plus you keep omega, you differentiate n effective, dn effective by d omega. So that is what we have written. And right hand side, what would be the variable? 2 pi is constant. Variable could be m. M varies from 1, 2, 3 discrete variations is there. That's why for differentiation, instead of dm by d omega, what we write? Delta m by delta omega, because delta m is discretized, discrete values. And then you know this value is nothing but group index. We have discussed earlier. So in that case, what we do? We can write this one, L, maybe we can write a little bit, L by C Ng equals to pi delta m by delta omega, right. Now if delta m equal to 1, That means successive resonance if I am considering. This can be written as omega, m equal to 1, whatever result for omega you are getting, that is a resonance frequency for omega 1, m equal to 2, omega 2, m equal to 3, that way you can get the resonance frequencies. Now, if I simplify this one, I get L by C, this one equal to mg, and right hand side pi delta m by delta omega. Suppose I want to get delta omega, that is the separation between angular frequency because of the successive resonance. So, that successive resonance means one, if it is m, next resonance is m plus 1. So, if you subtract this one, delta m will be 1. So, if we put 1, then this delta omega will be called delta omega, that means called as a free spectral range in terms of angular frequency. And if this is delta omega equal to linear frequency, if you consider 2 pi delta nu. So, that means we can write this one equal to pi delta m equal to 1, 2 pi delta nu, and that will be this delta nu will be called as a FSR, free spectral range, free spectral range. Okay. So, pi cancel 1 over 2 delta nu. So, this delta nu if I call as a FSR, so FSR can be written as delta nu equal to C by L to Ng, Ng is there. So, free spectral range. You remember that we have considered FSR for, we have derived FSR for micro ring resonator C by NGL. L, that case is a ring resonator perimeter, total perimeter, and in this case total round trip is 2L, that is why same expression is coming. So, free spectral range you are getting. That means you can get a resonance wavelength like nu m plus 1, nu m plus 2, and nu m minus 1, different order of resonance frequency I can consider, right. And if I just subtract nu m plus 1 minus nu m, that will be your delta nu, that will be called as a FSR. So, this FSR is actually C by NGL. If you have Ng is frequency independent, then the separation between resonance frequencies, that they will be constant. As long as Ng is constant, L constant, C constant, C constant, everything constant. So, their FSR will be only L dependent or Ng dependent, but they must be constant. So, we can see there a Fabry-Perot cavity modes. Through this path, if I just see that nu m satisfying from this equation for a certain m, is if it is resonance, then you can get neighboring nu m plus 1, nu m minus 1, nu m plus 2, 3, 4, so on, and this side also order will be m minus 1 starting from all the frequency. And you can see these are the actually resonance frequency, these are the point, they are resonance frequency and their separation is FSR, and FSR exactly equal to C by 2 NGL, right. And if you see, this is the cavity intensity, or in the transmission you can see this much it will be transmitting depending on the cavity. Here you will be getting this type of transmission, and depending on the loss inside you can see that instead of single line it can be little bit broadened also, that you can see. So, the problem here is, if you want to, this is a very nice device, it is a replacement of ring resonator, but one problem is that you have a mirror, you have to use a mirror. If you want to use a mirror at the edge, it is very difficult to integrate mirror at the edge of the waveguide, and you want to integrate it in a photonic integrated circuit. Because mirror, mostly it is a metal mirror or dielectric, different type of technology required. It is very complicated to fabricate in a microelectronics technology. Okay, but you can demonstrate. Maybe if it is a single individual waveguide and mirror, you can deposit at the, you polish the end face, and then you can actually get a mirror, deposit a mirror you can get. However, this type of device, that is one technological problem, and another problem is that this type of mirror, when you fabricate, most of the time metal mirror or anything else, if you fabricate, they are actually almost same reflectivity for all wavelength. It's a broad wavelength. That's why we are considering broad mirrors. So, that is the reason all the resonance intensity, they will be at a equal height. Their intensity will be at a equal height. They are regular, their intensity will be equal height. So, periodic filtering you can consider, periodic filter. So, if your bandwidth new range is only this much, then you can say that only this much will be storing and other wavelength will be just transmitting or reflecting. That way it will happen. So, sometimes it is not very good for many applications because of multiple resonance frequencies. Sometimes you may need multiple frequencies, but many times it is, most of the times they are not very good for certain applications. So, what to do? If we can use a DBR cavity modes, you know DBR cavity R equal to reflectivity we have derived using coupled mode theory. This is the expression, amplitude reflection coefficient, where S is defined like this and delta beta in terms of omega, that is why R is frequency dependent. So, we can say that this is complex. So, we can have this reflectivity is frequency dependent, highest reflectivity around Bragg wavelength, and you can have a stop band we have derived. This is something like this. So, you have this type of stop band, you can get this is a stop band that will be reflected, and outside transmission not stop band they will be transmitting. So, that is why you can get a frequency dependent reflectivity around a narrow bandwidth. And since it is a complex, amplitude is a complex, so you can write A plus JB like that, R omega equal to A plus J omega things. So, you can have also amplitude as well as phase. So, that phase also frequency dependent, we can write like that. And if you just derive this one here, you just express like this, then we can get R omega like square root of A square plus B square, and angle phase phi will be tan inverse B by A. So, you can express this one and find the phase, right. This phase it will be, because minus j, that is why minus pi by 2 is there, and rest of the thing if you do, it will be tan inverse delta beta by 2s tan hyperbolic SL. And when delta beta equal to 0, that means exactly at the Bragg wavelength, then phi lambda b will be delta beta 0 means this will go. So, this will be just minus pi by 2. So, exactly at Bragg wavelength, the phase change is in a mirror minus pi by 2. I have put a question mark here. Normal standard Fabry-Perot, what is the length I know? It's a mirror to mirror distance. But here you have distributed Bragg reflector 1, distributed Bragg reflector 2, it can have a R1 omega, it can have a R2 omega, they can be Bragg wavelength can be matched, okay, but their bandwidth can be different. But I know that distributed Bragg grating structure, what would be the length? Can we consider from here to here? Because I know that any field goes, it exponentially decays at Bragg wavelength for example, or any other wavelength within the stop band and reflect back. So, it penetrates into the DBR, the field, then reflect back partially. Similarly, it will penetrate inside and reflect back partially. So, that means can we use L exactly this one? Obviously, we will be saying no, but you can use this value as long as you can consider that inside the phase DBR you have a phase. This phase actually takes care of how much path length you must be considering, that information is involved here. So, you can consider L and this phi you can consider, and same principle you use here. Then you can find a resonance wavelength. So, in turn you can get, suppose it is a typically I consider this is for example your DBR response, and you know Fabry-Perot cavity their regular resonances are there, but your mirror, this broadband mirror replaced by a mirror like this. So, that means you only this mode will be surviving in this particular example. Other mode, since the mirror is not giving any positive feedback reflection, so they will not be resonant, they are like a simple waveguide type thing you will be getting. If you have a relatively narrower bandwidth such that you are getting something like this, then you can really filter only a particular mode, okay, particular longitudinal mode. So, that is a beautiful. So, you can control the bandwidth. We know how to control the bandwidth of a DBR structure, we have discussed in details. So, design parameters you can just optimize, and you can actually design a length so that you can get a single frequency oscillations, right. Moreover, since DBR just a periodic perturbation within the waveguide, anywhere you can fabricate on the photonics chip. So this type of cavity, if you want for certain applications, it is very easy to integrate on chip using CMOS technology. So this is one of the important parameters, just a DBR Fabry-Perot cavity. Next I am going to discuss about very interesting application using DBR structure, that is actually add drop multiplexer. We have seen this add drop multiplexer you can demonstrate using ring resonator. You can have a ring resonator, you can have one bus waveguide, another bus waveguide, you can have lambda 1, lambda 2, lambda 3 and so on, and certain lambda 2, for example lambda 2 equal to lambda r, lambda 2 equal to lambda r, that will be stored, but it can be coupled back here. So that particular wavelength can be dropped. Same way, if you just launch here lambda r resonant equal to lambda 2, that will be again coupled and that will be coming here. So lambda 2, that particular information will be dropped, additional information with same channel carrier wavelength you can add here. So add drop multiplexer we have discussed earlier using micro ring resonator. We can use also DBR structure for add drop multiplexer, but how? That has to be integrated in a Mach Zehnder interferometer. You know Mach Zehnder interferometer, if you consider here and here, this is a 3 dB power splitter, 3 dB power splitter. It's a simple Mach Zehnder. Let us forget about what is DBR here. This is for example DBR structure. This is also a DBR structure in both the arm is integrated, and that DBR structure actually has some certain kind of Bragg wavelength that is same you have designed. If you forget about this DBR structure, any series of channels, for example your channel carrier lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, maybe multiple channels are coming, each of them are having information and they are destined for different locations. You want a particular location, particular channel, for example lambda 3 you want to drop, you want to take without disturbing other channels. How to do that? If you use a simple Mach Zehnder, what you do? Normally all the channels will come. If you have this 3 dB directional coupler is wavelength independent, then all the channels will be splitted into both arms, comes back here, comes back here, again interfere, and because this is 3 dB, this is 3 dB, identical balanced arm, so all the channels supposed to come here, all this supposed to come here. But what we did, we have a DBR structure exactly reflecting lambda b, Bragg wavelength. This one also reflecting Bragg wavelength. So what will happen? That lambda 3 that match to the Bragg wavelength, that will reflect back here. This will reflect back here and they will interfere, they will actually reproduce here. It is like a, for lambda 3 it is like a folded Mach Zehnder interferometer. So that means normal Mach Zehnder interferometer through 3 dB directional coupler is there, in between arm is there, but here this lambda 3 maybe up to here it is going and then reflecting back, that means it is like a folded, and then again seeing the same directional coupler and in the cross port it will be appearing here. So this lambda 3, if it is exactly matched to lambda b, that particular channel I can drop here and I can send to our particular recipient where you need that information. And here what you will see, lambda 3 will be missing. So I could drop. The interesting point is that in ring resonator you have a multiple resonances, but in DBR you can select particular channel, particular narrow bandwidth. That particular narrow bandwidth channel you can actually drop without disturbing the rest of the channels. What else you can do? I know that my exact path, the channel that can carry one more channel, lambda 3 is missing. That information is already sent to certain destination. What you could do, I can have same lambda 3 with additional information, maybe from that port I can collect from any other sender, transmitter, that lambda 3 along with that information I can just launch here. It can split again here. In the same principle it will reflect back and come back here. Lambda 3 will be added. So, I can drop a channel and I can add channel with same wavelength but with different carrier, different information. So, this type of device is actually very useful. It is called add-drop multiplexer, and widely used this type of device in optical networks. But as I mentioned, this is very important also for on-chip applications. If you want to drop a certain wavelength without disturbing other wavelengths, then it is very important device. We actually have fabricated such a device. You see, this is a similar type of identical structure. You see 3 dB power splitter, 3 dB power splitter, wavelength independent power splitter. Here one type of DBR structure you can integrate, here integrate, that will be reflected back. We could achieve. I have not shown here results, but if you want some of our published paper, you can find the details how it can be fabricated and how it can be demonstrated. Okay, with this I stop here, and let us see in the next lecture. Thank you very much.